Okay, so last video I spent, it seems like a lot of time ranting about stuff and then getting lost in stuff that's not super hard just because it's like late and my brain is fried. But, so we have another proposition to prove in this video before we move on to talking about an example of like finding classifying all groups of a particular order, which is actually kind of neat that you're able to do that in the first place. So let's suppose that the order of h is p squared. Then h is either isomorphic to z mod pz, or nope, p squared, or h is isomorphic to z mod pz direct product with z mod pz. And then, in particular, H is going to be abelian because cyclic group is abelian. Direct product of two cyclic groups is a direct product of two abelian groups, which is abelian. So for the proof of this, if you've seen a lot of group theory before, that you might think, oh, of course, structure theorem for finitely generated abelian groups, or just finite abelian groups. But no, let's not do that, because we're trying to make this as self-contained as possible. Even though, even in last video, I said there were a few things that you can prove for yourself if you hadn't seen them yet. But they're kind of basic facts about algebra. The structure theorem, that's a little more like, I couldn't just say, oh, go off and prove the structure theorem. I mean, I could say that, but I don't think that would be fair, because I think it'd be a little trickier than just being like, oh, just do this and then in a line or two you're done. So anyways, we're actually just going to prove this directly using the tools that we have at our disposal. Using the structure theorem seems like you're, at least for something like this, it's almost like too powerful, almost like the sort of, like you want the level of the theorem you're using to sort of match the level of the exercise. It's kind of like you can prove that the cube root of 1 is irrational using Fermat's last theorem. Like, that's completely unnecessary. But there are really kind of interesting proofs like that, where you can use a really powerful theorem to prove a very simple thing. But we sort of want to avoid that. Anyways, I'm going to continue so that I don't fall into the trap of last video where I just babble about stuff. So since the order, if we choose any element which is non-trivial in H, then its order is either p or p squared. Why are we using sigma here? I don't know. So if the order of sigma is p squared, then certainly the subgroup generated by sigma is going to be H, because the subgroup generated by sigma is a subgroup of the group H. But if it has, if the order of sigma is p squared, then this subgroup has size p squared, which is the size of H, and so it has to be equality. Okay? And so, in this case, we have H is isomorphic to z mod p squared z. So we're going to suppose instead that H has no element of order p squared. Okay, then choose sigma to be a non-trivial element of H, and we want to choose tau in, we want tau to be an element of H which is not in the subgroup generated by sigma. And of course, tau is not going to be, it's not going to be trivial either, because the subgroup generated by sigma is a subgroup, so it contains the identity. And so tau is, this set here does not contain the identity. Okay. we want to show, I'm going to write that as WTS, that H is isomorphic to the direct sum of these two subgroups, the one generated by sigma and the one generated by tau. Okay, so what do we want, or what do we need to show? So we're going to do this direct sum. We're going to use it in the direct product sense. So we want this to be a direct product. We want this direct product in the sense of semi-direct products, i.e. we want a semi-direct product such that the two subgroups commute with each other. So we need H to be equal to subgroup to sigma times tau. Of course, I mean the subgroups there. And well, okay, not and. We need the intersection of these two subgroups to be trivial, and we also need sigma tau to be tau sigma. And if we have sigma tau equals tau sigma, then the generator of this subgroup commutes with the generator of this subgroup. And so that means that all elements of this subgroup commute with all elements of this subgroup. And so this actually is enough to prove the normality. I'm not going to write all that out, but that's important to keep in mind. That this merely implies the commutativity of these two subgroups, rather than it by itself being enough. The last statement follows from abelianity, which I'm sure is not a word, but whatever, I'm going to use it. H is an abelian group, right? Yeah, we proved that last time. H is an abelian group. So that's obvious. So we need the other stuff. Sigma, let's see here. So sigma is a here. I'm going to call these, I'm sick of calling these things. I'm going to call the subgroup generated by sigma s and the subgroup generated by tau t. So the size, okay. So S intersect T. Intersections of subgroups are subgroups. We proved that. So S intersect T is a subgroup of S, and it's a subgroup of T. So we know that the size of the intersection divides it divides the size of S and it divides the size of T. Therefore, it divides the greatest common divisor of the size of S and the size of T. It's about to write a tau. Okay, well, what's the size of S? Wait, is this the right? This is wrong. This is not the right approach to be using. The approach I'm thinking is we're going to use it in the next part, but not here. So anyways, last statement follows from abelianity. If S intersect T is not equal to the identity, then the size of the intersection must be equal to P, right? Because it's a subgroup of S and it's a subgroup of T, so its order has to divide the order of S and it has to divide the order of T, but both of those are P, so its order has to divide P, So it's either 1 or p. If the order is not 1, which is the case when the intersection is not just the identity, then it must be p. Okay. Okay, and this contradicts. What does this contradict? The fact that tau is an H set minus subgroup generated by sigma, or I could have just said S. And why is that a contradiction? Right, because, okay, if we write that using S, okay, so if S intersect T has size P, okay, well, S has, S has P many things in it, and tau is chosen outside of that. This is obvious because we chose tau to not be an S. And so the subgroup generated by tau has at least one thing in it which is not contained in S. And so S intersect T is strictly contained in T, and T has size P. And so S intersect T, since tau is in H set minus S, the size of S intersect T has to be no more than P minus 1, because best case scenario, every element in capital T other than tau is contained in S. But that's the best case scenario. We're never going to get P many elements in S intersect T. Okay, so we have a contradiction to this. Okay, so thus S intersect T equals the identity. Okay? So we've got this and we've got this. Now we need this. Let's see here. Lastly, okay, sigma tau, we're just going to call this S times T. And this is equal to the subgroup generated by sigma and tau. Why is this the case? Okay, well, obviously we have, right, because what you can do with S times T is you can take any element in, this is any element in S and any element in T. Well, what that means is that we're taking some number of elements of S and multiplying them together, and some number of elements of T of... You can prove this inclusion both ways if you want. If you have an element of S times T, then you write this element as sigma to some power, you write this as tau to some power, and obviously that's going to be contained in this subgroup, because this and this will generate that element, because you just multiply this by itself a few times and then this by itself a few times. Now if you've got an element in here, then you use commutativity. And so if you've got like some, algebraists call these words, but just like a string, words that was, just a string of symbols where you've got sigma and tau raised to different powers, and those powers can be any integers. Then what you do is use a Booleanity to just put all the sigmas together and put all the taus together, and then bam, you've got something in S times T. And so that's why we have this equality. Let's see here. So this has order strictly greater than P, or rather, so this is such that the order is strictly greater than P because it contains S and it also contains tau, which is not in S, so it's at least size p plus 1. And because it's a subgroup of h, which is size p squared, it must divide p squared. Okay, so what numbers divide p squared and are greater than p? Well, p squared. And so, S times t must equal h. Thus, in this case, i.e. in the case where h has no element of order p squared, we have concluded that h is equal to, well, I'm going to write it as z mod pz squared, because it's really just the direct product of this and this, which is just, this is z mod pz, this is z mod pz. Of course, when I say is, I mean is isomorphic too, but I mean this is group theory. We'll just call them the same thing. So yeah, that finishes this proposition. And after this, we can go on and actually talk about some actual groups of specific orders and go from there.